Good afternoon, everybody. My name is Deborah Brisbane. I'm with RISA Technologies, and we're going to be talking here about using RISAFloor for commercial building design. Thank you, Amber, for the introduction. Let's talk a little bit here about some of the products we have here within RISA software. RISA 3D was one of the top programs on this list here, and that's one of our most popular software packages out there. It's a three-dimensional finite element analysis software tool. General purpose, you can use it for anything from designing a frame or a building to a roller coaster. It's kind of the sky's the limit with RISA 3D. And a lot of people are very familiar with that program. RISA 3D and RISA 2D are identical programs. RISA 3D is going to be a three-dimensional, and RISA 2D is just going to cut out that third dimension. What we're going to talk about a lot today is this RISAFloor on the top left portion here. RISAFloor in particular is going to be geared towards building design, and today we're going to be talking about commercial building. And what we're going to see in RISAFloor is that we're going to lay out a building floor by floor in plan mode here, so we can draw in a plan view, and then we'll lay out our gravity system and our lateral system, columns, beams, walls, all things like that will be laid out, and we'll design that the gravity loads down the building in RISAFloor. We'll take just the lateral elements into RISA 3D for the lateral design. We also have a program called RISA Foundation, and in RISA Foundation you can actually take that same model from RISAFloor into RISA 3D and then into RISA Foundation for the foundation design. RISA Foundation will also do foundations just on its own too, without the model running all the way through. We have some other smaller programs here called RISA Foot, which is a footing design analysis program. We also have RISA Masonry, which will do masonry, walls, columns, and lintel design. We have RISA Base, which does base plate design. We have RISA Section, which is a section properties program. And then at the bottom there we have a RISA Tower, which is a tower analysis and design program for monopoles and self-supporting and guide towers. So those are kind of the suite of the different programs we have available. But what we'll be talking today here is focusing specifically on the commercial buildings. We have today's agenda kind of listed out here on our screen. And what we're going to be talking about, first of all, is some of the design criteria you can use to optimize your beam selection in RISAFloor. We're going to go in depth in the joist design and joist girders, basically how we're actually doing that joist design and girders. So what we can see is a little bit more insight of how RISAFloor is doing that, so you can really get an optimal design. We're going to talk about a new feature we have in RISAFloor, which is sloping roofs. And we'll talk about all the different ways you can slope your roof. We'll be talking about composite design in here. We'll be talking about, specifically in RISAFloor, how to control your composite design and what results you'll get out of the program. We'll be talking about vibration analysis, and that'll go through here as well, how to lay out your vibration analysis and then exactly what kind of results you can get. And then we'll go through the entire RISAFloor and build a model so we can see some of these features that I've mentioned above in action. So let's talk a little bit starting out here with the design criteria. What we're going to do to set up our design criteria is using something called design rules. And what we can see here on the right side of my screen is that you have the data entry toolbar. There's a design rule tab, and you can click on that, and it will open up this little spreadsheet here that will help you limit what your design criteria will be. So you can change you can control your member design based on the depth of the member, the minimum or maximum depth. You can change the width of your members, minimum and maximum, and then you can also change the maximum code checks. So a lot of times in projects, people will come in with initial loading, and they won't know the entire loading on the structure. So you may want to limit your member checks to maybe 90% instead of the full 100%, so that when you get loads updated later, you have some capacity to grow into that. This is not just for beams. This would also be for columns too. So you can set up any one of your members to have these criteria. The other thing you can do is control your deflection. So in building design, it's very typical that you'll have deflection criteria for your floor system or your roof system. And in RISAFloor, you can control the fact that you can have a dead load deflection, either a maximum in inches or a ratio, a live load deflection, or the combination of dead and live load. You also can choose some different categories. Maybe you're not doing dead load and live load, you're doing dead load with a combination of roof live load, things like that. You can actually change those categories and take a look at that too. Let's talk a little bit more about the joists here. So in RISAFloor, you can design joists. You can lay out joist girders, and you can lay out single steel joists. And the way RISAFloor takes that loading, we're going to apply a uniform area load to the entire model. And to analyze that joist, or to design that joist, what we're going to do is turn that area load into a distributed load per joist. And the way we're actually going to do it is take it into a uniform distributed load for dead load, a uniform distributed load for live load, and then we're going to turn that into a total load. And we're going to go directly into the SJI tables with those. So what you have there, so you can actually pull those numbers, and we're going to see here at the bottom of your screen you get a UDL, an actual UDL, an actual ULL, and an actual UTL. Those are the totals and the dead loads and the live loads. And that's giving you there. And then when the capacity, that's pulled right out of the table. And then we see here what the capacity of that joist is. So you can actually see, pull these numbers directly out of RISAFloor and make sure that you see the joist that you're looking at for the capacity. One thing that's important to note is that none of these uniform loads include the other load category. So we have dead load and live load, and there's other categories available to you called other load, and that won't fit into these uniform dead loads and live loads. So we do put a nice note on the top of the screen, OL loads not included in a joist design, so you know that going right off the bat. Also, it's important to note that the load combinations are not used in creating these uniform dead loads, uniform live loads, and uniform total loads. So your load combination isn't really going to make a difference. So if you are trying to factor things with those combinations, you should actually directly put the loads onto the joist there inside of the dead load and the live load, area loads. So you actually get those out there. Talk a little bit about special loading. So whenever you have a joist that has non-uniform loads, either point loads on the joist, or we see here on the top right we have some taper loads on that joist. This is what we call non-uniform loading. You're going to actually get a special joist call out. And that special joist is going to be a big alert to you that you do have some loading that is kind of outside the boundaries of what the SJI tables have here. So it gives you a note, and what you'll see is when you have the output, we'll see here an SP in parentheses for that for you. And you'll look on the RISAFloor output, you can see that listed there. But what we do for design, we're still doing that design on that joist, but the design is going to be based on the capacity of the shear envelope of the joist under a standard uniform load. So if you look on the right side here, this is what we have here is the shear envelope. It shows you in gray outline how this shear envelope actually works out. And this is calculated here. Backed out of these tables, calculated, and you can actually find these calculations in some of these Velcraft. This is from designing with Velcraft, steel joists, girders, and steel decks. And you can actually calculate that envelope diagram. And we're going to actually superimpose that envelope diagram directly onto a special joist. And that kind of sees it out here. So let's take a look at an example of how this works. So if we look at a joist with special loading, this one has a 30-foot span, and we see 2 point loads at 1/3 span. So we have one point load here of 1.5, another at 1.5 at 10 and 20 feet. What we're going to do is we're going to call this out as a special joist, and we're going to kind of fit that shear diagram directly on top of the shear diagram that is the actual shear diagram. So this is the calculated gray diagram that we just saw previously from those calculations. And what's important to note is that the maximum shear is not the critical point of design. So the maximum shear on this joist above here is 2.486 kips. And that's actually not the point that's controlling this design. When you look at this overlay, what you can see is really at this corner here, that's where the critical point of design, where you have that pointed into it. It's basically, that's where we're controlling the design. So you may question, say, okay, how come that joist is being designed that way? And that's exactly where it's being designed by this little critical point of design. So this is how we do our special joists. We also have the ability to lay out joist girders in RISAFloor. And girders are called out based on the assumed depth. So it's kind of assumed that what happens in girders is that you tell the program that you're going to have a 28-inch depth girder, and then what the program will do is it'll actually size here, it'll call out for you that 28-inch depth girder. It'll give you the corresponding number of equally spaced concentrated loads. So on the bottom of our screen we can see here that we have 6 kips plus 23 kips concentrated every time here, 8 different times on this girder that we're looking at. And then the last number tells us here the magnitude of that concentrated. So basically these two numbers are added up to give us 29 roughly kips every 8 for 8 increments there. And that's the kind of call out that you're actually going to give your joist manufacturer. So we've got that all listed out here for your joist girders. A similar thing happens for joist girders is that you can have a special loading situation. And the top of this picture here shows us directly that we have maybe 29.2 all the way across, but then we have a case where we have one extra load here, maybe 33 kips is coming in for one time. And that's actually going to alert the manufacturer that SP call out, or that special joist girder, is going to alert the manufacturer of that joist that this is a special configuration. And we have this listed out here. The joist girder actually, and any kind of joist girder is going to actually, when you go into a special configuration, you're probably going to pay a premium on that. So you're going to want to make sure that you are specifically not just having a little spike of load, something maybe small. So what we have here in global parameters is something called joist girder load tolerance. And what that allows you to do is set the maximum load variation to be allowed when specifying that joist girder call out. So what we can see here is it's got listed as 0.2 kips. So what that means is that if this little spike of load went above 0.2 kips between the rest of the other loads, we're going to call it out as special. But maybe you don't want to really go, if you're in a case where it's maybe 0.5 kips, something smaller there you can actually say is justifiable. But you wouldn't really want to make that tolerance too large, because you do want the folks who are making that girder alerted to that. So for joist girders, what we're going to do here is calculate the moment of inertia. So when you tell the program in RISAFloor, you tell the program that 24G, which we saw here on the top right corner here, that means that it's the 24-inch depth of the girder. What we're going to do is use this estimated moment of inertia to help you get your deflection calculations. So we're going to go through the deflection and find whether that works for deflection criteria. And this is the calculation we're going to use for when you just call out the depths. You can see you get the beam length and then the joist girder depth in there. When you tell the program specifically what you're going to be using, so it's got a lot more information, this calculation changes just a bit. Gets a little bit more accurate here if you're going to tell it exactly what's happening. So you need the joist spacing and the point loads, and it will actually calculate all the information there to get you a little bit more of an accurate estimate for that moment of inertia. But you can tell the program either way. Okay, once you've got all that information, it's going to be reported to you in the detail report. So when you look up in the detail report, you're going to be able to find the self-weight of the girder that was used, and you can also find in here the the IZZ, or the moment of inertia for that girder. So some common questions that we get is, how are my joists being selected? So what you've got here, the first thing that I always think of is it's going to be the span is going to be the number one thing that's going to be selection-based. So the span is actually going to go right into the tables. And what you'll see in those tables is some numbers, and we'll see in the next slide coming up here, is that sometimes you will have areas of the tables that are not filled out. And the tables seem to be things that what they've done is they've gone through and said, what's the most economical for this configuration? And sure, they can make things above and beyond those tables, but this is the economical portion of it. And so that's what we're going to use, is we're going to use what span. So on this one here, we have a 25-foot span, so we picked out a 14K1. We also need to meet the capacity. That's the number 2 thing there. So that would be, we have to make sure we hit the capacity for that span. And then lastly, we're going to make sure that we hit the right joist weight. So we're going to try to optimize your joist weight and bump through and find the best weight for your joist. If you also see here on the bottom, how do we get these 2.5K2 get selected at the bottom of our screen? And what's happening there is that the spans are below 8 feet, which means that they're not available in the K-joist tables. So 4 foot to 8 feet, you get a special range of K-joist series called 2.5-inch K-series joist substitutes. And that we're going to actually use those for those smaller ranges. So a lot of times if you even go below 4 feet, you're not going to get a design. And maybe they can make these special joists for them, and we can actually force that to happen and explicitly call out one for you and check it, but the program's not going to pick that for you since it's outside of the boundaries of the table. We also hear, so this is continuation of that, how that joist is being selected. So this 14K1 we were talking about with the 25-foot span, It's going to, based on its capacity, what is its UTL, or uniform total load, is 115 kips per foot for this span that I have shown here on the left. And what we picked is that 14K1, and that's 180 kips, 180 pounds per running foot as its capacity. And you can see from the table that there may be a 12K5 that would work, but there's nothing actually filled in that table there. So what we're going to use is the next one available, which is the 14K1. Okay, so you've got kind of look through the table and make sure you understand how those are being picked. So you keep going here. So other common questions is, can I analyze an existing joist? And that's a really good question. What we're basing things on in RISAFloor is design, but you really can analyze things that are already there in place. And the way you would analyze them is you would lay out an explicit shape. You would tell the program to be using an actual 14KS, for example, and we tell it to use this explicit shape. And this is coming in through our modifying the beams properties, and we'll see that when we lay our model here in RISAFloor coming up. And on the right side here, you can see you can choose from any of the series we have available, K-series, LH, DLH, SLH, KCS. Any of these series we can find specifically a joist that we want to use and explicitly call it out. And that's how we would do an analysis of that joist. The next topic I want to talk about is some of the new feature we have is with sloping roofs. In this slide, what this really helps us see is that we can slope the roof in any different direction. Specifically, these roofs here on the bottom right, we just see kind of a pitch, one directional pitch there, pretty simple. But then we start to see some really nice complex roof systems that we can do in RISAFloor now. We can do kind of a hip system here on the bottom left corner. We've got directions in multiple directions. And we can also do a sloping in the roof in more of a pyramid format that we see on the top. So the sky's the limit on what you want to do for your actual sloping. It allows you to give you flexibility to create any type of geometry you need. One of the ways you can do that actually here, and when we'll see when we do this ourselves, but what you can do is you can just define your rise versus your run, so which is a very nice typical roof system. So just say rise versus run, maybe 4 on 12. You can define an angle. So you can tell the program just to pick an angle, and then you can choose maximum height. And that may be something where your architect gives you the maximum height on one side of the building, and then you don't have to calculate a rise versus a run, things like that. It's pretty easy. The other way you can do that is just to elevate a series of points. So that might also be a way you can tell your architect can give you just that whole series of points is such and such offset or elevation off of a certain height of that floor level. And you can just lift that whole area quickly and easily without having to calculate an angle. So we'll see that in action coming up. Another feature here we're going to talk about is composite beam design. And what we see here is some of the ways you can control your composite parameters. In your global parameters here, you've got a list of different ways that you can actually control this composite design. You can tell the program whether you want to use non-composite if optimum. You can tell it to use uniform studs only. We can tell the different levels of composite we want, how many maximum stud spacing we want. We can also even tell the program whether we want some end offsets before we start the studs, or how many of the width for 2 rows or for 3 rows, what the minimum width would be there. So you probably want to visit here your global parameters before you get started with your composite design. And then what we can see, the program actually can do things like uniform studs, which will tell us here in the parentheses when we get results on our beam. It will tell us here whether we have studs in parentheses. So we'll see here 54 studs are right now in this beam, and then it has a camber listed below that. We can also see segmented studs. So we see number of studs shown in every segment. So for a girder, for example, each segment, okay, which is in between each beam framing in or joist framing in, you have a segment, and it's going to optimize that directly inside of those segments. Maybe you don't want to do such an optimization and you want to do your own. You can actually manually change these studs using the redesign tool. So you can come in and choose what beam you want to be using. Then you can choose what uniform studs. And just by toggling back and forth between uniform studs or segmented studs, you can type in the specific amount of studs that you want to be using. And what's really nice about this feature is that on the top portion of the screen here, it's going to tell us whether these amount of studs, what happens during bending checks, during our shear check or our deflection checks. And maybe that's what's actually controlling the design. Maybe deflection is what gets controlling rather than actually your bending, for example, which is a really, really good clue to how to design that member. So we'll use this when we actually build our model too. Vibration analysis is one of the really powerful things too in RISAFloor. You can get your vibration analysis for your model, and that's a really common thing for a commercial building. We've got here, it's going to be based on the AISC design guide, and that's based right in your global parameters. Here you can see that. You can put in your damping, and you can use your AISC design guide 11. What we're going to do for your vibration loading is going to be, it's going to be based on the self-weight of the members and the deck. And that's automatically calculated for you, okay? And we're going to see how you can adjust those self-weights there of the deck, and we can actually up or down those self-weights if we need to. And the vibration load is going to be added into that, and that's what we call here, a vibration load is what we call as a superimposed dead and live load. And you may want to adjust that superimposed dead and live load. That's basically, we're not going to take the pre-composite load and the post-composite and the live load and make an assumption that that's your vibration load. So right here in your uniform area loads, you have the control to change that vibration load to be whatever combination of superimposed dead and live that you need. And once we have that vibration load, you see that listed right here, we're going to actually apply that to the members as uniform distributed loads per section 3.3 described there in the AISC design guide. So we're going to actually lay that out, and you're going to get results on this vibration in the detail report. You'll get full results, and we'll see that. But one of the greatest results here, I love to see this, is color coding. It's a really, really good way to see how the whole model is working together. We can see color coding based on acceleration, which is on the left side, and you can see here we've got a little color-coded chart telling us all the different values of the acceleration. And then we have here based on frequency in hertz here, and we have a little color-coded chart, and then you see all the beams color-coded based on where they land on this, this little index. So this is a really nice way to see how your model is actually behaving. So now that after we've talked a lot about all the different pieces we have and features that we have in RISAFloor, let's build this model and see how we actually use those in practice. So I'm going to jump over to RISAFloor. And in RISAFloor here, it's going to start out with a model. We're going to actually ask you to start with a floor level. So first floor, we're just going to title it as first floor as a label. And we're going to tell the program here the elevation of this first floor. So first we're going to say it's going to be 12 feet. We're going to give it a default area load of office, and a default deck is going to be switched over here to composite. Let's start with composite on the first floor. So the deck angle I'm going to leave as 0, and I'm going to say OK. And starting out here, you get a project grid to start. You can enter your model in with a DXF import. You can use a Revit structure as an import. But we're going to start from scratch and build the model in RISAFloor. So what I'm going to do is I'm going to lay out 3 at 40, which is in increments of 3 increments of 40. And then I'm going to use a comma and type in 38, and it's going to generate 5 different project grids for me in the horizontal direction. So I can see here I've got all these different project grids. They can actually be adjusted if I needed to directly on the screen once they're created, but I'm going to go right over to my x-axis and start them here. And in my x-axis, or my vertical direction, I'm going to type in 4 at 28 and say generate. And I see here that I've got 5 different project grids and with 4 increments of 28. And then I can adjust this from here too, so I can enter anything in there. What I'm going to do is go ahead and add some extra ones in just to help us guide our model a little bit. So then I can say insert a new line, and I'm going to tell the program here, once we've inserted this line, I'm going to tell the program to label this B.5 because it's going to be right after B, and I'm going to tell it to be going 14 feet from that location. I'm going to tell it to go after the current line. So if I say OK, I can see here that right after B, I get B.5, and I'm at 14 feet directly after that. And behind my screen here, you can see it starts to populate right away. I'm going to go back to the Z-axis, or the horizontal direction. I'm going to add in another one in here called 4.5. So I can use the right-click command and say insert a new line, and then I'm going to tell the program to call this one 4.5. And the distance after this one, I'm going to tell it to be 20 feet. I'm going to also say to place this line after the current line. and it's going to go right in there at 4.5. So if I close my project grid, now I get to see how the project grid laid out. You don't need to use a project grid, but it's very helpful to help lay out our models when we start out. So first thing I'm going to do, this is a three-dimensional model, but we're looking at it in plan view. So what I'm going to do is lay out the things that are below this plan, so it helps support the model. So first thing I'm going to do is going to say I'm going to lay out walls. They're going below this level. So if I draw a new wall, I click on this. This is going to be a shear wall is what I'm going to be drawing in here. And it's going to be from the bottom level is going to be the base, and that's going to be then going to the first floor, which we defined here as 12 feet. And I tell the program here that I'm going to give it a general wall. And I'm going to tell the program also to use a lateral function, so it's going to be a shear wall. I'm going to tell it to be using a 4,000 concrete normal weight. And then the thickness of the wall, I'm going to leave it 12 inches. And so I can say apply, and I can just draw anywhere I want on this project grid. And that's why it's so helpful to have your project grid laid out. Actually, I'm going to draw this directly across here, and I'm going to lay it out like that. So it's basically going to be my little elevator bay on the right side of my building. The next thing I'm going to do is draw in some lateral columns. So if I click here on the lateral columns, draw columns, I'm going to lay out some lateral columns for my brace frames. So in RISAFloor, when we open up the draw columns, we see here that we have hot rolled, cold form, wood, concrete. We can design from any of these different items. I'm going to choose hot rolled, and I can say material to choose to be A992. The shape group here, instead of telling the program that I'm going to be using a specific column, like maybe a W8x10, I tell the program I'm going to use a family or a shape group. And this is where the program is going to go through a long list of different shapes and inside of this shape group and pick one that works. So for the demand that's in that area. So I've got here, I'm going to tell the program to use a wide flange for these columns, and I'm going to be lateral. I can orient them in any direction, but right now I'm just going to default to their orientation, and I'm going to say apply. And I'm just going to draw in some columns around my building, and these are where my brace frames are going to be going into in just a second here. So I'll lay out those in a second here, and the rest of them I'm going to lay out all my gravity beams. One of the cool things about RISAFloor is when you go back into this dialog, you see that you don't have to do anything else. It remembers everything you just did. All you have to do is go back to gravity and click on apply. And now it remembers everything we had in that setting. So I can just click, and by clicking on the grid intersection around here, that's as easy it is to lay out a column. It's really fast. And so I have all my columns around the exterior. Now I'm just going to lay out some ones on the interior. Maybe this one's a little off-center, and the rest of them here I'm going to line up. Okay, so I've got all my columns in place. The next piece I want to do is lay out my lateral beams. So let's finish off our lateral system just by clicking on the Draw New Beams. I open up this beams, and I have, again, the same options as I saw before, hot rolled, cold form, wood, concrete. We could do any of these different types of materials. I can do steel products for my joists or wood products for wood joists. But I'm going to choose a hot rolled A992 this time, and I'm going to choose it to be lateral. And it's going to automatically default to having it oriented around the strong axis. And I'm going to have it be pin-pin because these are going to be braced frames for me. And composite, I'm going to have this floor be composite, so I want to make sure I have that composite checkbox on. As soon as I say apply, I can just click and then on the grids, and all of a sudden here I get my beams in place. So I have my beams already in place. I have for my lateral system, I'm just going to finish off my gravity system. So if I click on Draw New Beams, and then I switch it over, like I said, it remembers everything we just did. All I have to do is switch over to gravity, say apply, and I can just rubber band here around a couple of these real fast, and I can see them all quickly populate on my screen. So I've got all of these in place. I'm going to just finish off a couple of these connecting the walls. Okay, and we can see here this goes right against the wall, and I close out this elevator bay, maybe have some openings in there for our deck. So we have all of our major beam system laid out, but what we'll want to do is have our more repetitive framing interiorly here. So what we call that is infill framing. So if I click on Generate Beams Within a Bay, I can click on the hot rolled again. I'm going to switch over to the A992, keep the composite flag on, and wide flange is my shape group. what I'm going to tell the program is to space these composite beams every 8 feet, for example. So we'll be spanning between 8 feet. I'm going to tell the program which direction I want it to be. So horizontal will be for one area. I'm going to say this will be horizontal, and I can just rubber band around the entire area, and then boom, it pops right in there. So I have all these beams already placed, and maybe this side of the building, let's say we have some HVAC going the different directions. So what we can do is just turn that to be vertical. We could have also gone in any direction of a beam, an angle, if we had an odd area in our building, but I'm just going to click on that and close this off for this area. So you can just click within a bay, and that's just as easy. So the next thing here that I'm going to do is I'm going to lay out I've laid out my gravity beams. I've laid out my infill beams. I'm going to go ahead and put in my slab edge. So I'm going to click on here, create or modify an edge perimeter, and I click on that. And I just tell the program what my edge overhang distance should be. And then we have ability to do both rigid and flexible diaphragms. I'm going to actually keep this as a rigid diaphragm, and all I have to do is say create a slab around the perimeter, and just say apply, and around the entire perimeter of the building, that slab goes in place. I can also do is add some openings by going right back into the same spot, into the create openings, and then just say create an opening perimeter, and click right inside of those for my elevator bays. So now I have some openings right inside of there. So lastly here, once we have a slab in place, we actually have a default deck running right across our model once the slab is in place. And I'm going to use here one of my new toolbars I have at the top of my screen. I'm going to show here what it looks like to my default deck. So if I click on this, show the deck, and it's going to say with the default, the deck is now running across my screen. So the deck direction is very important for load attribution. What's happening is that the deck is running perpendicular to the beams, which means that those beams are being loaded with their tributary area there. That makes sense for the right portion of my building, horizontally, going perpendicular to the beams. But on the left side of my model, that doesn't make a lot of sense because my beams are actually running in the different direction. So what I'm going to want to do is place a deck on top of that to override the default deck. So I come up into here and I say assign a deck or a slab, and I click on that, and I just tell the program now to use a composite deck, and I tell it, let's use it parallel to the vertical or parallel to the x-axis. And all I have to do is say apply, and then just box this area where I want this deck to go on top. So this deck is actually overriding right on top of that default. And if you look at the bottom of my screen, you can see here where it says composite deck. Let's see if I can highlight that. Right down here, we see no deck is available right now. But if you look at the screen there, if I go when I move my model down here and I move my mouse around, you can see it says composite deck 90 degrees. That helps me see that it's which way it's running, and that's our big clue at the bottom, exactly which way it's running. So I've got all of that laid out for my deck direction. Let's talk about what the deck actually has as the defaults. So if I click on the deck definitions, I'm going to open up that spreadsheet. That's on my data entry toolbar, the third item down. Right here we have a composite deck, and this is the default deck that we have laying out right now. It's a composite deck. It has a thickness of concrete there of 3 1/4. It's using 3,000 F'(C) concrete. Okay, you've got a weight of 110 pounds per cubic foot. Excuse me. We have an elastic modulus called out. We have a maximum span of 10 feet, and then its unbraced length right now is at 2 feet. So we have all this listed in for our general properties of this composite deck. If I go over to the composite tab, this is where I can define the rib height. I can tell the rib top width, the bottom width, all that information, the pitch of these ribs. I can tell it the stud's height. Right now we're at 5 inches. If I need to change the stud diameter or the stud strength there, I can change all of that. I can tell the program whether it's short or not. I have all that ability right there in that composite tab. Now, loading tab, this is where the self-weight of this deck is going to be calculated. So when we talked about vibration loads, things like that, right there, that self-weight is right now at 50 pounds per square foot, or 0.05 kips per square foot. Okay, you've got that for the self-weight of this deck. So wherever this deck is, we automatically are putting this much self-weight on there for you. and we have some construction dead load if you needed to put in that there, and then we have some construction live load automatically in this defaulted. You can add to this list, so if you wanted to, you can say add to it, and that's something you can add anything you want to it. You can also do is you can save some of these decks. So if you're working with decks all the time, you can come up to the default button at the top here, and you can choose default. So as soon as you set up your own parameters the way you want them to be, you can save that to your model and click the default button. So then when you start a new model, you'll have your defaults all set for you. So you won't have to recreate those every time you go in there. So that's real helpful too. You can also here, so I'm going to close out there. So we have our deck in place, and what we have in our floors, I'm going to open up our floor spreadsheet. If I click on that, we had told the program right when we started, we opened up that floor, we said first floor is going to have an office load for its area load default. It's going to have a deck of a composite deck, and the angle is going to be 0 degrees. So that office is another thing that area load is being defaulted right now, is called office area load. So let's review that for a second. So right below here, the deck definitions, you have area load definitions. I'm going to click on that and take a look at what office loads mean. So right here we have office loads as our label. We can have a pre-composite dead load, which would set up there right before you have your composite behavior. You have your post-composite dead load. Right now I have 10 pounds of post-composite dead load. I have live load of 80 pounds per square foot, and that live load can be determined to be either live load reducible, non-reducible, live load special. We can do roof live loads, snow loads. We have shedding snow loads, and we have rain loads. We have all these different abilities to change our different live load types. The vibration load is something we mentioned earlier, but we can change that vibration load right there. So that's the superimposed dead and live that you want to be counted in the vibration calculations. And then the dynamic load. The dynamic load is something that gets calculated for the superimposed dead loads that are above and beyond the self-weight of the members and the actual deck. And you can tell the program here what to be using for that seismic mass. This is what we call our dynamic load. Right now this is set at 0.75, and we'll leave that there. You also have the ability to put the other loading in here. So you can things maybe that don't fit into this dead load and live load categories, we can go ahead and put in them, call them other loads, and tell the programming directly what kind of direction you want to put that in the global direction of Y, the local direction Y, or the projected Y. Okay, so you can actually change that there. What we're going to do while we're here, let's add a roof load, live load. So I'm going to add this to be called roof. I'm going to say this is going to be for our later on for our upper levels. I'm going to put in 10 pounds of square foot in there, and I'm going to put in 20 pounds of square foot for my live load, and I'm going to change it to be roof live load reducible. And I'm going to give it a dynamic loading maybe of 10 pounds of that. So it's just my superimposed dead load that I'm putting in there. So I'm going to close that spreadsheet now. And we already had that area load already put on for us. The next thing I want to talk about, what we talked about before, was design rules. And let's click on design rules for a second. So for our members here, what we're going to say maybe is that this is going to be a typical design rule. And what we're going to say is let's limit the maximum depths of our members. So we don't want the members to go above 28 inches right now. So no matter what, there has to have 28 inches for our maximum depth. We won't give it a minimum depth, but we'll give it a maximum depth. Okay, and we could have adjusted our deflection, but these ones are pretty much set up the way that the IBC requires, so I'm going to leave that there. But we had mentioned that earlier. This is where we would control that. So the next spot here, let's add another floor to this level. Okay, so what we can do is say insert a floor. So we can insert another floor. We can just do is copy that first floor. It's just as easy as saying copy the columns, the beams, the edges, the decks. You can do anything like that and copy it directly up. All of that information will be copied up. We also could have used a child and parent relationship. Now the child and parent allows you to have an exact replica. The child will be an exact replica of the parent floor. And what's nice is that if something gets changed on that child floor, on the parent floor, the child floor gets changed. But vice versa is not true. So maybe you have some extra point loads on your child floor. They will not get carried to your parent floor. So that's a really good behavior use as well. I'm going to say just use a copy of the first floor for now, and we're going to say 24 feet, and I'm going to say office and composite again. And I'm just going to call this second floor before we get off of this. Say second floor. And I can say OK. And I can see that everything got copied directly up the building. Let's just double check that this is a three-dimensional model. Okay, so it's a full, when we look into the top left corner, we say full model view. It goes to the three-dimensional model, and you can take a look at this and spin this 3 dimensions. It's just as easy as looking at in RISA 3D, for example. But all it is it's just that what we like to see is so it's uncrowded view here on a plan view. It's so nice to be able to work on one floor at a time. So I've got this extra floor level up here. What I want to show you on this floor is a couple things that we didn't mention on the lower floor is that we can add any kind of loading to this model. So what I can do is I can say, let's apply some distributed loads to it. And we can apply some dead loads. Let's apply maybe 1 kip. And this is going to be maybe a tapered distributed load there. And the dead load post composite. And I can apply it anywhere I want to on the model. If I turn on this universal snap points, it lets me click basically anywhere on my model. If I look in the isometric view, I can see that this guided me kind of along the distance of multiple spans over multiple beams. So what I can do is I can maybe use on the bottom right corner of my screen, I see that there's dimensions, and I can actually it'll help me set up directly where I need to be. Otherwise, I can go on a beam if I wanted to. I can go directly on a beam. So you can place this anywhere. The other thing you can do is put in point loads. I can assign point loads to this model just by maybe, let's put some live load point loads on here. I can say 1 kip of point load can be placed anywhere on this model. So I can just click around the building and place it either on a beam or off a beam. That's all set up right for you. So I can see that on 3 dimensions as well here. I can go into and look at an isometric and see that. So you have point loads ability, you have line loads ability. You also can even do your own area loads. You don't have to use those area load definitions are for the entire structure, but we can go ahead and put in uniform area loads anywhere on the building just directly, or we can do tapered area loads, maybe for snow load, for example. You have a tapered area load. You can do that with a maximum magnitude and peak magnitude there, a base magnitude and a peak, and you can put all that information in. So I'm going to leave that there. The next one I want to do, I want to insert a floor and put that rooftop in. Let's use some of those joists we talked about a lot. So what I'm going to do is insert another floor, and I'm going to say let's copy the same floor, but this time I'm not going to copy it in my loads or my decks or my openings, and just copy the rest. And I'm not going to extend the walls up. If you notice here, I was copying those walls directly up, and it was being by this checkbox right here. It says copy or extend wall panels from below. This time I'm not going to extend those wall panels. So I'm just going to go to 36 feet, and I'm going to use this roof load that we had just made here, that default area load. We're going to click that roof one. The default deck, this time instead of a composite deck, what I want to do is use my metal deck. Okay, and the direction is going to be 90 degrees for my default, for my deck. And I can say OK, and a couple windows open up here. Let's just switch over to our level there. So what we've got here now, this is our roof level. We didn't copy those walls, okay, and we have a lot of our beams and columns coming across. So what we'll want to do is maybe get rid of some of this topper portion of the model. I'm just going to keep this left portion of my model as my rooftop. So what I'm going to do is select just the right portion. I'm using my selection tools, and I'm just going to highlight a lot of this area on the right. And what I'm going to do is say delete, and I'm going to delete items based on what's selected. So I'm going to say delete based on this criteria, delete my selected beams, and delete my selected columns, and I can say apply. And then what it gives me a message, it says, do you want to delete the single floor of the column or the entire column stack or the entire current column lift? And what I'm going to tell it is just this top floor. That's all I wanted to delete here. So I'm going to say just remember this answer and remove just the single column and say OK. And now it's gone. So now the rest of my building here is just on this top portion. And now we still have composite beams in place here. So what I want to do is I'm going to unselect the lateral beams because I still want those to stay, but I really don't want any of these other composite beams. So I'm going to just say delete again and delete based on this criteria and say delete the beams. And just say apply. And now we just see the columns. And if I select all, we didn't delete those lateral members anymore. However, at this level, this is not going to be composite. So there's a couple ways you can uncheck the composite. What I like to do is go over to the beam spreadsheet, click on the beam spreadsheet, and switch over to hot rolled. And I can see that there's a composite flag, and that's what tells the program whether it should be checking composite design or not. So what I like to do is just say click on the composite, the entire row, and just right-click and say fill the block with it empty, so it unchecks that composite flag for me. So now the same beams are in place, but they just don't have composite design. So I say okay, and I can close that up, and now I'm looking directly at my model again. What I'm going to do now is lay out some of the exterior beams. So I'm still going to use hot roll maybe along some of the exterior of my model. So I can say use a gravity. This is going to be A992. I'm just going to make sure to remember to uncheck the composite flag, and I can just draw some hot rolled around the exterior here. Now these ones along this direction, I'm going to keep these as girders. So let's go back in and draw new beams. And what we're going to do this time now is go and use our steel products. So when we switch to steel products, we have the shape group available. Remember this from our slideshow here, shape group, and then we have the custom joist girder grouping. We're going to tell the program that we want to be using 28G, okay? So that's the 28-inch depth girders, and I'm going to click on that. You could tell the program here to choose just joist girder, but it's going to sort of size it based on the weight. And that's not typically what people do in the industry. You usually know what depth you're going to be allowed for clearance. And so you're going to want to probably set up one of these and not let the program try to optimize on weight for girders. Girders are one of those things where you just always know what your actual maximum clear height is going to be there. So we're going to give it 28 depth there, inches for the girder. And I'm going to say apply, and I'm going to draw that directly across there. And we see here it actually doesn't mess with our lateral beam. It just goes right across and it skips that. And I can click this all the way across, and it goes right across and skips that lateral beam. So you can actually draw two beams on top of each other. It's sort of smart that way. That lets us draw directly across things and doesn't double the beam for us. So I've got those, and I'm going to put one in the middle, and I'm all set for that. So now I have 3 rows of girders. Just so if you ever get confused, you can click on this Members Labels button. And by the way, I'm using all of my brand new customized toolbars. If you don't have these available, you can go into your Tools Preferences, and you can go into your Tools Customized toolbar. This is another really new feature, and you can set up all of these newer toolbars. On the left side would have been the new ones that you don't have there, but you can add, and just push Add button directly onto there. And you can see mine has already been added, so they're all there. What's also really nice about this feature is you can rearrange some of your toolbars. So things maybe you don't use a lot, you can pull them off the current toolbar selection, and then you can rearrange them so you can see them the way you like to see them on your screen. So I like to use a lot of these, and then one of the great ones here is this member one. We can see the member shape group that we're looking at. So we can see on our screen we did 28G, and that's really helpful to know that we drew that correctly. The next one we're going to do is lay out our joists. So we've laid out our girders. Let's lay out our joists. I'm going to click on the Generate Infill Beams. And if I click on here, what I'm going to choose is going to be steel products. And the steel products, again, you're going to choose from one of these long lists here. You have the DLH. Now you can choose steel joists. But again, typically you're going to tell the program what series of joists to be using. I like K-joists, so I'm going to use K-joists for my series. And I'm going to tell the program to be equal spacing but not to exceed 4 feet. And I'm also going to tell it to go horizontal across my screen. So if I say OK, and I apply it right directly there, I just click inside of the bay. I get K-joist spaced 4 foot on center. So I have all my joists in place. The last piece I want to do is lay out that slab edge. So if I click on the Create a Slab, and this time I'm going to lower the overhang distance on the slab so it doesn't pick up so much. Here, maybe 6 inches, and just say Create a Slab. Goes around the edge. There's really not a slab. We talk about slab edge, but it's really a deck edge perimeter too. It's kind of the same name for 2 different things. So we've got a deck edge on this one. Since we use that default deck at 90 degrees and we don't have anything else running, we don't need to define another deck on top of there. What's really nice and fast is that default is in place already for us in the right direction. So we're all set. We don't even have to address it. If you did put it on top of it, it wouldn't hurt. It would just go directly in the same on top of it. Just extra work you don't need to do, though. So we've got that all in place. The last thing here, I'm going to turn off my deck so we don't get distracted. The last piece is going to do sloping. So the new sloping tool is right here. It's right next to the infill buttons, and it says change the elevation of the selected points in the model. So if I click on that, what I get here is just like the tool we saw earlier. It's got the rise and the run, and we're going to choose maybe a 1 on 12. Okay, so we can choose that. If we wanted just to elevate the points, we had that option. It's just by switching tabs you do that. Oops, got to type it one more time in here. So 1 on 12. And what it tells us to do is says select 2 reference points to define the base plane of the roof. Okay, so what's getting raised is actually the columns. So it's going to be looking for a node here or somewhere I can click to that I can actually select 2 points or a plane that is defining that slope. So what I'm also going to do is I'm going to unselect the entire model, and I'm going to select just a portion of my model to slope. If I slope one side of my model, the other side is actually going to get sloped just right along with it. Okay, these are going to get carried up, and those beams are going to come up for the ride, and we'll see that right now. So with this tool, I click on one point, and then it gives me this big red line across my screen. And what it's looking to do is create a plane. So if I tell it the plane is this direction, it's going to slope anything that is selected 1 on 12 from this plane as the base point. So I click on that point, and let's see that I did that correctly. We zoom in, we see that I defined 1A to 1E as my plane, and it went up 1 and a 12 on each side. And I can see that that other side got sloped right along with it. It gets really nice to see that there. So if I show it rendered, it helps me see how that actual columns got lifted in the center. It's just as easy as that. So it's really easy to do that sloping. Okay, I think we're done with all of our modeling. We are all set here. I'm going to go back into the rendered view, and we look in 3 dimensions, and we can see our model here with our sloping roof, with our rest of our composite beams, and I'm going to go back in a plan, switch over maybe to 3rd floor again. And now I'm going to create load combinations. So if I go into the load combinations here, dead load and dead load plus live load are already in here, but we did some pre-composite and post-composite stuff in here, right? We had some self-weights, some going to be pre-composite. We want some of the composite behavior done. So what we're going to do is click on the load combination generator, and we're going to choose United States as our region, but we could have changed from any region. IBC 2006 ASD is what I'm going to want to use there. And I have some roof live load, so I'll check that. I didn't do any snow or rain, so I don't need to check those. Pre-composite and post-composite, I want both of those options. So I click on Generate. And then I see here that we have some pre-composite loads, some live load construction. So this one's really important for my pre-composite behavior. And then I've got all my rest of my loading here. So I solved the model, and it's running through the solution here. We can see solutions iterating behind the scenes. And it's designing every one of my members. Hot rolled all of my composite behavior is being done right now. And we've got a solution. Okay? So with the solution present, what we see is every member is now designed. If there wasn't any problems, the warning log would pop up and tell us, for example, something didn't work. There might be a maximum span violated, or one of these members didn't work. So what we can do now is let's look at some of our results. We have 24K4s listed for all of our members for our joists, and let's take a look at those results. So let's click on one of those joists. And in particular, in this joist, we sloped this member, so we're getting a projected length versus what the beam slope is with reference to the actual floor elevation. We see that it's a K joist. It tells us here. And if I click on, now this is important in RISAFloor, make sure you click on the load combination or category to get what you want for the diagrams. So you click on load combination and maybe click on dead load plus live load if that's one of the ones that you're looking at, and we can see what's actually happening in the model. And so you actually get a different loading here for your projected. That's a really nice important thing. In parentheses, you're seeing a little bit of different loading happening in there for the projection. If I scroll down below, you get your shear and you get your moment and your deflection. But what you really have, and what's really important here, is your total load and, your point loads if we had any. We didn't put any point loads on this one. But you have your distributed dead load and you have your distributed live load. And that's going to be, if we scroll all the way down, the total joist load here we saw before is going to give us, we're at 75% capacity. We have the total loads listed out in the uniform loads, and then we can see what the total load capacity of that actual joist was called out. We even have here the deflection criteria, and it tells us how well we did. So we're at 87% capacity for that one. And then we have our end reactions. So this is where you're going to go through and take a look at all the different members. We saw that this one is actually giving us some special joist behavior because we're basically above and beyond that level there for that joist. So we're getting some specials happen on this one. And if we scroll below down here, we can see here the deflection. We see that joist girder data, and we see the deflection calculation there for us. So we've got all this for our joist information. We can explicitly call out one like we said we could do that, but let's look at our composite behavior. So let's go back down to the first floor. And we can see on this first floor we have all of our beams are called out now, 14 by 30s, a lot everywhere. We see that we've got 54 of our studs in parentheses. I'm going to click on one of these shapes, and this is the detail report which I keep on clicking on. Detail report right here on the left corner. You click on it and you can click on any beam and get the full details of what happened during the design. So if I click on that and I scroll down a little bit, what I see here is I have a length of 40 feet. I can go and see how much load got on this member. If I scroll down, it's my moment in shear diagram with my deflection. There's no slope on this one, so I don't see any axial loads. If I scroll below that, what I get here is a lot of information on my composite behavior. First is the loading, then we get the design rules, which we said it was a maximum depth of 28 inches right there. I have a shear. I have 27% shear capacity. I've got non-composite bending, okay, and that's going to give you from my pre-composite loading. When it goes into composite bending, it tells me here a lot more information about what I've got for my B effectives. It tells me what my percent of composite is, all the different composite sections that I have. And then lastly, it's going to give us our deflection criteria here. So it's going to give us our capacity, what the ratios were, and what the total deflections are, the reactions. And then at the very bottom, this is the vibration analysis stuff that we mentioned earlier. You get all the vibration analysis, different items in here from the code check. One of the pieces we also mentioned is that you can take a look at the vibration on your screen. So to do that, you just go into plot options. And when we're in plot options, we have the ability to show things for us on color basis. And so when we look at color basis, we have a long list. First one is kind of an interesting and good way to look at your members is a unity check color basis. And if I just push apply, and I close some of these down here, you can see that there's a code check little dialog here on this. So when it's green, it's going between 0.75 and 90. So those are the ones that are pretty stressed out here on the right side of my screen. They're highly stressed compared to the rest, which is all pink, which means, pink is actually getting even higher here at 0.9 to 1, so everybody's even more stressed over here, which is good. I'm running to higher to capacity, which means I'm designing at the limits, which is very good. Let's see if we go down below this. This is what I really like to see is the vibration acceleration. Say apply, and we can see what we've got here. If I look at this, it's going to give me the color coding of my vibration acceleration. And then if I look at here, I can see vibration frequency. Say OK, and I can take a look at what the frequencies are for each beam there. So you've got all that information based on color coding. Otherwise, when you look at it standardly, you're looking at gravity versus lateral. You're always sort of looking at that blue versus red, which is just gravity versus lateral. The other thing I want to mention, too, is the redesign button. So when we were clicking on the detail button, we were looking at a lot of information of the post-design. The redesign button, or the design button on the left corner, really helps us dial in with this composite behavior. So if I click on one of those members there, I'm looking at M19, which is right down here. What we've got here is it's designing it at 14 by 1430, a W14 by 30, and we can change the uniform studs. So how come 48 studs didn't work? Well, a long list of things is why it didn't work, right? We see here that we're failing in deflection, we're failing our shear transfer. Okay, so let's maybe optimize that. We can click on the optimize button and pick ones that worked. What if we check on the unflag composite flag? What does this beam work? Now what would be the optimal beam? That would be a 24 by 55. Okay, so that composite flag is actually really helping us. We can click on that. So you see, well, the different things that are happening, but maybe we said, hey, that 14 by 30, I just don't want to use that. I really want to use a 12 by. I wonder if a 12 by 40 will work, and it will. So a W12 by 40 will work, and we could use that instead. And if you wanted to, you could just say okay, and it will replace that for you. So now we've explicitly called this out as a W12 by 40. So once you've dialed in your gravity design, you've got all of your different information set up, you can use the director button at the top right corner to direct over into RISA 3D. If I click on RISA 3D, this is going to be where we're going to be going into our lateral design. So for the lateral design here, we can choose the ASE 705. I can choose the occupancy category, maybe as a 2, and I can choose the wind speed based on the area that I'm in. So if my local area, my jurisdiction says 90 miles an hour, I'm going to say that, and I can say calculate the loads. And here it's going to give me the wind generation input. It's going to give me all the different factors here that go into doing the wind calculations. If I scroll down below that, I can see each floor level is going to get a leeward and a windward load. And it actually comes out to, in the model, we're going to see forces in the X and the Z direction. These are point loads that we're going to see in our model here in just a second. And they're going to be applied into each different level. Two different point loads in each direction there for, let's see here. So I'm going to say okay. And that's our wind loads that we just saw. Now we're going to see our seismic loads. So if I choose a code under my seismic loads, I can choose ASE 7 2005. I can choose a CT, maybe change this to be 0.02, for example. I can type in 0.02. My R is a little iffy because I use a little bit of a mixed system in here, but maybe let's use a 6, for example, for my R. And let's see, I have my SD1 I'm going to type in for my region. I would find this up in my IBC. I'll look up what I'm using, and maybe 0.16, and maybe I'll use a 0.27, and then a 0.1. And if I say calculate the loads, all of the different information gets calculated for me. This is basically coming in off the top of the information that I put in. Okay, oops, let me give myself a TL there. Okay, so we've got all that information placed in. And then now what it does is it calculates the period for me. It calculates the base shear and then tells me the governing equation that was used. It tells me here each floor level what the weight of the structure is for each floor. It tells me here the the center of gravity and the forces in each direction. We're also going to be placing this seismic load directly into the diaphragm at each 3 of the levels. So we're going to look for a force in the X direction and a force in the Z direction. 3 different forces, and they're going to go into each direction there. And we're going to see this is going to go actually into the eccentric loading. So we'll see that we're looking at a little bit of eccentric plus and minus there. So if I say okay, let's look at this. The way this always makes sense is to actually look at the model and see how it gets applied. So when you come into RISA 3D from RISAFloor, the only thing that gets transferred is your lateral members. So just the lateral frames and just my concrete shear walls. Now, a little scary at first. You think, hey, where's the rest of my model? Don't I need it? Well, anything that was actually applied to these members are here. So if I click on turning on the loads, I see that there are the loads here. So every one of those joists that we're framing in at the top there, and then the composite beams below that, the loading from the dead load and the live load are still there. Okay, and then the top we saw that it was roof live load that you've got there, so you can get roof live load on that top level. So all that information still got carried across. But what didn't get carried across was all those members, because we really don't need them for the lateral design. They're just there just for reference. And if you ever really want to see them when you're inside a RISA 3D, you can go into the Plot Options tool. You can go over to Miscellaneous, and you can turn on Show RISAFloor Gravity Elements. This is for rendering only. So if you say OK and you click on your Render button a couple times, you see that these members actually pop into your model. So it's not the end of the world. You still got those members there for you. Okay, so what we can do is turn that off and just say uncheck that and say turn it off. What also got calculated is all of our wind loads and our seismic loads. So if we take a look at our wind loads in the X direction, we see here, and it says on the bottom corner here, it says wind loads in the X direction. We can see that those wind loads are actually being applied to each level. Let me turn the diaphragms on too. So we can just see the outline of that diaphragm placed on our building. Okay, and each floor level is getting now an actual load in the X direction from the wind loads in the X direction. We also can see here, if I turn this onto the wind loads in the Z direction, we can see that we've got wind loads in the Z direction at each floor level. So you've got all that placed into the diaphragm for you. Turn that off. so we don't have those distracting us. But what you see is you can apply those point loads directly into your model. They're automatically calculated for you. If we look up the basic load cases spreadsheet, we see that we have three loads per each different category, in the wind load in the X and the Z with the partial wind loads, as well as the earthquake loads in the X and the Z with the eccentric loading there. So you got eccentric directions there for you. So that was all automatically placed into our model. The last piece we have to do in here is put in our brace frames. So I'm going to click on Draw New Members. And then here, you specifically tell the program what type of member to be using. So instead of telling it to be using a shape group of a wide flange, what I do is I tell it to use, for example, maybe a double angle. And maybe I pick some random size right now, because we're going to check it, and the program is going to give us a better suggestion probably here. So I'm just going to pick something off that list. I'm going to tell the program what design list to check, though. So I tell the program specifically, RISA 3D, please use a double angle, but I don't want you to suggest a wide flange. I want a suggestion of a double angle. So I need to pick the design list that I'd like the suggested shape to be based on. I'm going to use grade A36. And now if you are going in and back and forth between Revit structure, this is probably your most important piece from when you're going into RISA 3D. Make sure that your braces are called out as vertical braces. Revit structure is very important that Revit structure understand between beams, columns, and braces. So I'm going to call it a V brace. I can say apply, and I can draw in a brace in any different direction. So maybe for those long ones, I do real long braces. Maybe here for shorter ones, I can just do something strange. You might want to have done that reversed, but that's okay. And looks like I can draw some of these in. And one of the things here, let's see, I can click on those, and I can draw these from there. Okay, so you've got all those members drawn in place. And the last piece you can do is create load combinations. We created load combinations in RISAFloor for gravity loads, but now what we'll really want to do is load combinations in here for RISA 3D. So if I click on LC generator, what I'm going to do here is I can pick the entire wind loads. I can tell it to go all the way from X and Z, or with eccentric, or even with quartering. And I'm going to go the whole way here and give it all the different load combinations and just say generate. And when I do that, I see that I get a long list of different load combinations automatically generated for me, 93 of them. And what I can do is, let's say for speed and to get this model going here, we're going a little over time here, but I want to just check some of these and make sure we can get some suggested shapes. I'm going to turn on some of these different load combinations, and all I can do is just turn a couple of them on and then say solve the envelope solution. An envelope solution is going to run through every different load combination. It's going to give me the worst case of each different load combination and tell me the reaction, well, what happened in each different load combination, the worst minimums and maximums. So if I look at the results here, one of the things I want to do is go to my design results. And in design results here, I'm going to want to look at the models here under code check. So right now I have some failures, and you can see that they're turning red. So that means that they're failing. And I even have some compressive failures down here in some of my angles. So what I'll want to do is I'm going to want to redesign this model. I'm going to do it with my suggested shapes. So click on suggested shapes. I can see here that I have a long list of items that it's suggesting. So some of them are smaller but heavier, okay, and then some of them here are going to be bigger actual shapes. So it's going to run through a long list of different shapes that the program is suggesting for us. So the way I can solve this is I can either click on this button up here, replace current shapes, or I can right-click and say solve again with current shapes. And I can run the model one more time. It gives me a little warning message because what's happening is the model is getting rerun. The whole stiffness matrix is being rerun with another solution with these different members in. It's going to clear the results. And do I want to continue? And I can say yes, continue. And then I can rerun the entire model. And as it goes through these different load combinations, we can see that there's still a couple members that it's suggesting differently. So if I click on the design results, I see this is sort of an iterative process. We're still not doing that badly, though, for some of these, but we still have some suggested shapes. So you may want to solve it one more time, solve it. We're going to just do it twice today here and see where we come out. But it's going to be a little iterative because you are changing the way the loads are being distributed. So let's take a look. So it looks like we're just a little overstressed on one of them, and I'm going to stop there for our time's sake here. But what you get in here is you get your code check. It tells you what the shear checks are. It tells you all the different factors that went into it, and then at the very end it tells us what was the actual controlling governing equation used for that member. And then we can click on here and take a look. So what I'd like to do right now is just run one load combination and see. I'm going to solve one load combination, and we can take a look also at the detail report right in here. So if we look at our, just like we had in RISAFloor, we have the detail report, which really does give us a lot of information on this one load combination, telling us why or why not things worked. And here we can see our axial, our torque, if we had any. It shows our deflection and our shear moment diagrams, as well as our stress behavior below here. These are all interactive here in RISA 3D, so you can kind of work with those and see if there's something odd happening in between there. And at the very bottom, you get the code check information. So in RISA 3D, this is really just a one-page, quick way to know a lot of information about that one member. And this would help you actually design that members if you're having some failures going on in there. The other piece I want to make sure we see is that if you click on one of those walls we drew, in the concrete walls here, you're going to get a lot of analysis information ready for you to go into reinforcement design. So you've got your axial forces in here for this wall. You've got your moment and your shear diagrams for both in plane and out of plane. Okay, so we're calculating both for you right there. And you can see just a little bit of out of plane here because we probably didn't run one with much. But what we've got here is for each wall element, you're going to get that. If you're using masonry, we're going to give you all the reinforcement design. And if you're using wood shear walls, we're actually going to give you the shear panel design. And we're going to give you the hold down design in there too, which are brand new features. So once you're finished with your design in here, you can use the director button. Also, just to make a mention too, if there's any loads above and beyond that you didn't account for, you can come in here and load up that lateral system. You can either load it into the diaphragm, you can load it into just directly into a frame or into a wall and add things like that. So I'm going to go back into RISAFloor, and all of the members got resized. So these members here, these 18 by 55s, were resized in RISAFloor. They come directly back into RISA 3D, resized as well. So from RISA 3D. So you don't have to worry about any of the lateral design. Comes right back into it because we're still in one model. We haven't really left this one model, and that's what really gives the power of RISAFloor and RISA 3D is that all the information is contained in this one model, and we can see that in the RISA 3D there. So we're here. Let's jump back to our PowerPoint here for a second. Let's talk about some final things to consider about RISAFloor. So we did that model by just drawing it from scratch, but the thing is to mention is that you can import and export geometry directly from Revit Structure. We have a webinar coming up if Revit Structure is something that's important and that you're using or want to learn how to use. We have a webinar coming up on May 27th, and that will be the complete integration between RISA and Autodesk Revit Structure, and we'll be focusing on the 2011 link that we're going to be putting out there in May. So that's a really good webinar to review, as well as we have you can import and export with DXF too if you're not using Revit Structure just yet. The other thing is what we have is one model. I mentioned that at the end here, but it's really important that you see the power of that one model is going in for both gravity, lateral design, and you can even take that model into RISA Foundation to get your full gravity and lateral design for your foundation. We also will have another webinar in August based on that. It will explain to you kind of the comprehensive design of shallow foundations with RISA Foundation. That's going to be a really powerful presentation showing you all of the strengths that we have in RISA Foundation. So I hope you do have be able to join us for that. And you can find out more information on all the webinars. These are just two that may be of interest, but we have a lot listed on our website.